In section 3.7, we want to look at limiting reactants, and we're going to start with an analogy. And the analogy is baking cookies. So here on the left, we've got some ingredients that we can use for making cookies. We've got some butter, some sugar, some flour, some milk-like substance, and some eggs. When we look at these ingredients, of course, one of these ingredients we're going to run out of first before we run out of the rest of the ingredients. And of course, the ingredient we would run out of first would be sugar, right? If we're going to make cookies, cookies have lots of sugar in them. We have enough sugar there to make a couple of cookies, but not very many. Now, we will ignore the fact that we do not have any baking soda here. We'll assume that the baking soda is in good order. So the ingredient that we will run out of is sugar. That means sugar, in the terminology of doing limiting reactants, sugar is our limiting reactant. In other words, it's the thing we run out of first. All the other ingredients would be considered excess reactants. So the butter, the flour, the milk-like substance, and the eggs, those would all be considered excess reactants. So let's look at a limiting reactant example. Again, our limiting reactant is the stuff that is there in the smallest stoichiometric quantity, or it's the stuff that we run out of first, if we want to put it in layman's terms. If we look at this particular reaction between hydrogen and oxygen, we'll see that we've got 10 molecules of hydrogen on the left and also 7 molecules of oxygen. Whereas on the right, after all the reacting has occurred, we've got 10 molecules of water and 2 molecules of oxygen. Well, the thing that we ran out of first is hydrogen. So it is the limiting reactant. Hydrogen is our limiting reactant. When it comes to the excess reactants, that's any other reactant that is not the limiting reactant. And so in this case, oxygen would be our excess reactant. So what we want to be able to do is we want to be able to calculate the limiting reactant, and we also want to be able to determine how much of the excess reactant is going to remain after the reaction is over. Now, it's quite simple if we're just counting up molecules and separating them out and making new molecules. But when we're working with grams, as we always do in the lab, then that means that we need to look at this from a different perspective. So, in order to determine the limiting reactant, we need to do a couple of stoichiometry calculations. We'll do the stoichiometry calculation from each reactant to one product. The good news is you get to choose which product it is. And often that choice will be pretty simple because it will make sense which one you should choose. In addition to that, the limiting reactant is going to be the calculation that gives you the smallest amount of product. The amount that you get is going to be the theoretical yield of that product. So you just do the calculation, and that will give you your theoretical yield by looking at which one gives you the smallest amount. So we're going to look at number 73 on the in-class assignment, and I've got it set up here, number 73. And we'll go ahead and read that. We've got, so it says, the fizz produced when Alka-Seltzer tablet is dissolved in water is due to the reaction between sodium bicarbonate and citric acid. So sodium bicarbonate and citric acid. So here's sodium bicarbonate, there's citric acid. We've already got a balanced chemical equation. Here is carbon dioxide is one of our products, water, and then sodium citrate is our other product, and we're not very concerned about it. In a certain chemical experiment, 1.00 grams of sodium bicarbonate and 1.00 grams of citric acid are allowed to react. Which is the limiting reactant? Well, this is a pretty straightforward problem. We're going to take each of these and do a stoichiometry calculation from each of these, because we know each of these quantities, to one of our products. Now, which product? Well, if we look at part B, it tells us which product we're going to need to know the theoretical yield for. So we're going to use carbon dioxide as our target. So when we're doing this calculation, I'm going to set up the roadmap for each reactant to that product. So we'll do mass of sodium bicarbonate to the moles of sodium bicarbonate to the moles of carbon dioxide to the mass of carbon dioxide. Okay, and we're going to do another calculation that's very similar, this time from citric acid. So the mass of H3C6H5O7 to the moles of H3C6H5O7 to the moles of carbon dioxide to the mass of carbon dioxide. So before we do the calculation, I just want to say that if sodium bicarbonate is the limiting reactant, then that means the answer to this calculation will give us the theoretical yield. If citric acid is the limiting reactant, then the answer to this one will give us the theoretical yield. The way that we'll be able to tell which one is the limiting reactant is which one gives us the smaller number. And we don't know that until we do the calculation. So we have to do the calculation. All right, so let's go ahead and start. So we'll do 1.00 grams of sodium bicarbonate. All right, so mass to moles, we need to use the molar mass of sodium bicarbonate. And I've got my periodic table here. Let me look at it. So 22.99 for sodium, plus 1.01 for hydrogen, plus 12.01 for carbon, plus 3 times 16 for oxygen. And we get 84.01 grams of NaHCO3 per mole of NaHCO3. All right, moles to moles. Moles to moles, ratio. The ratio here is the ratio in the balanced equation. And you'll see that we've got 3 moles of each. Now, I'm going to write down 3 moles of each. So I'm going to write 3 over 3. Even though you could theoretically write 1 over 1, I'm going to write 3 over 3. That way, when I come back and look at my problem later, if I need to do that, then I will be able to identify where I got those numbers, because they came from the balanced equation. If I put 1 over 1, I may not recognize where I got the 1 over 1 from. All right, and then finally, moles to mass, molar mass. The molar mass of carbon dioxide, we've done this one several times, and it is 44.01 grams of CO2 per mole of CO2. And that gives us a number. So I'm going to clear all that out. We'll do 1 divided by 84.01. All right, and here I'm going to. We don't even have to type in those 3's. We can just cancel them out. And while we're doing that, we'll do dimensional analysis. Grams cancel out. Moles of bicarbonate cancels out. Moles of CO2 cancels out. All right, so I'm at this point. This is 1 over 1, so that's good. And now we're just going to multiply by 44.01. So times 44.01. And you'll see that gives us 0.5238. And we have 3 sig figs, so we'll call that 0.524 grams of CO2. All right, so all that tells us is if sodium bicarbonate is the limiting reactant, then this is our theoretical yield. But we won't know for sure until we do the other half of the calculation. All right, so 1.00 grams of H3C6H5O7 And then we need the molar mass of H3C6H5O7. I'll go ahead and calculate that, although I do have it written down over here on another piece of paper. But we'll go ahead and calculate that. We've got 3 plus 5, so 8 times 1.01 plus 6 carbons, so 6 times 12.01 plus 7 oxygen, so 7 times 16.00. And we get 192.14. So 192.14 grams of H3C6H5O7 per mole of H3C6H5O7. All right, now for moles to moles, we use the ratio. And the ratio here is carbon dioxide to citric acid. So there's CO2, there's citric acid. It's going to be 3 to 1. So 3 moles of CO2 for every 1 mole of H3C6H5O7. All right. And then finally, from moles to mass, we'll use that molar mass, 44.01 grams of CO2 per mole of CO2. We'll go ahead and do the dimensional analysis real quick. So our grams of citric acid cancels out, our moles of citric acid cancels out, our moles of CO2 cancels out, and that's going to leave us with our grams of CO2. We'll clear all that. We'll do 1 divided by 192.14. All right, we'll hit enter, times 3 times 44.01. And that gives us 0.687. So 0.687 grams of CO2. All right, so now all we need to do is compare these two numbers. We're going to play a game that I call which one's smallest. This one, that's the smaller number. See, isn't that a fun game? That means this is our theoretical yield. And since that's our theoretical yield, that means this is our limiting reactant. And that's really what it says, which one's the limiting reactant. So sodium bicarbonate. Now, if we want to, we can say this one is our excess reactant. That's the other information that we get from it. Now, we've already answered this. How many grams of carbon dioxide form? Well, it should be whatever that theoretical yield is. So the amount should be 0.524 grams of CO2. All right. For part C of this problem, when we look at it, we see how many grams of the excess reactant remain after the limiting reactant is completely consumed. Well, we need to do two calculations here. One, we need to do the calculation from our limiting reactant to our excess reactant. And so we're going to do mass to moles to moles to mass. All right, so we're going to do that calculation. And that will tell us how much of the excess reactant was consumed. So let's go ahead and write out the roadmap for that. So mass of NaHCO3 to the moles of NaHCO3 to the moles of citric acid, and I got a little carried away and started writing the wrong thing there. It's okay. So the moles of H3C6H5O7 to the mass of H3C6H5O7. Okay, so now we just set it up. We've already got our molar masses here. So we've already calculated those, so that part's easy. So 1.00 grams of sodium bicarbonate, 84.01 grams of sodium bicarbonate per mole of sodium bicarbonate. Mole to mole is the ratio, and our ratio here is going to be 1 to 3. Again, we're going to use the coefficients in our balanced chemical equation. So 1 mole of H3C6H5O7 okay, and let's see, 3 moles of CO2. All right. Oh, and I put the wrong thing. I was being distracted by the train in the background. I don't know if you guys can hear that, but it was distracting me. Fortunately, I have some white out there. So NaHCO3. All right, finally, we'll do 192. So our moles to mass is the molar mass, and that is 192.14 grams of H3C6H5O7 per mole of H3C6H5O7. All right. Let's do a little bit of the dimensional analysis to make sure everything cancels out. So our grams of sodium bicarbonate cancels out. Our moles of sodium bicarbonate cancels out. Our moles of citric acid cancels out. And that's going to leave us with our grams of citric acid. Now, just as a reminder, this is going to tell us how much of the citric acid was consumed. It does not tell us how much is left over. But once we get this number, we'll just subtract that from the amount we started with. So 1 divided by 84.01, enter, divided by 3, enter, and then multiply by 192.14. And we get 0.762. So 0.762 grams of H3C6H5O7. All right, and here I'm going to put a note, consumed. All right, when you do this stoichiometry calculation from your limiting reactant to your excess reactant, it tells you how much was consumed. It does not tell you how much you have left over. In order to get the amount that's left over, we'll do the very simple calculation of subtraction. We started off with 1.00 grams of citric acid. We consumed 0.762 grams, and the amount that we are left with is the difference between those. So 1 minus 0.762. And that gives us 0.238 grams. Now, there's one additional thing we need to do before we have this as our final answer. We need to pay attention to significant figures. Hundredths place, thousandths place. When we're doing subtraction, it's the place. So we're going to round that to the hundredths place right there. So our answer is going to be 0.24 grams of H3C6H5O7 remaining. All right, and that is our limiting reactant problem. Now, if you're thinking, oh, I need more practice at that, don't worry, you'll have some on your homework. And in addition to that, we've got another one here where we'll have to do a limiting reactant problem as well. Okay, so we're going to go back to the presentation, and we're going to talk about the theoretical yield just a little bit more. The theoretical yield is the amount of product that can be made when you are doing this reaction. So it is the amount that can be made. In other words, it's the stoichiometry problem from the limiting reactant to the product. All right. This is different than the actual yield. right? Because and you, if you've done any lab stuff, you already know that there's the amount that you think that you're going to get, and then there's the amount that you actually get, and often that amount that you actually get is significantly less than you thought you were going to get. So the actual yield is different than the theoretical yield. So we can do a calculation to determine our percent yield, and the percent yield is going to be the actual yield divided by the theoretical yield times 100, and that times 100 to make it a percentage. All right, so let's go back to the in-class assignment here, get everything lined up. All right, we've got ethane. It says ethane reacts with chlorine. The main product is C2H5Cl, but other products containing chlorine, such as C2H4Cl2, are also obtained in small quantities. All right, the formation of these other products reduces the yield of C2H5Cl. So we want to make this chloroethane, and we don't want to get the C2H4Cl2. So we want to minimize that. Calculate the theoretical yield of C2H5Cl when 125 grams of ethane reacts with 255 grams of chlorine, assuming that C2H6 and Cl2 react only to form C2H5Cl and HCl. Okay, I'm going to write the balanced chemical equation up here. So we'll do C2H6. Now, I just happen to know that these are all done in the gas phase, so I'm going to write gas, but that's not very important here. And I'll go ahead and put a space for the coefficient. Here we've got chlorine, so Cl2 gas, and that produces C2H5Cl, also gas, plus HCl, which is also a gas. Well, if you go through and look at this, you'll see that this is already balanced. We've got 2 carbons here, 2 carbons there, check. 6 hydrogens, 5 plus 1, that's 6. 2 chlorines, 1 plus 1. So this one is already balanced if we use coefficient of 1 for everything. Now, of course, you don't have to write the ones. You could just write that as it is. So here we go. We've got 125 grams of this. So 125 grams of the ethane and 255 grams of the chlorine. And we want to find what is the theoretical yield of this. Well, we don't know which one of these is the limiting reactant. I mean, we could say, well, maybe it's this because that's a smaller number. Yeah, but that's also a lighter molecule. So really, the only way to do this is to do the stoichiometry calculation. It's not too terribly difficult. I'm going to set it up so that we write out the roadmap for each. So we'll start with this one. So we're going from mass to moles, moles to moles, moles to mass, and then the same thing, mass to moles, moles to moles, moles to mass for this. So our mass of C2H6 to the moles of C2H6 to the moles of C2H5Cl to the mass of C2H5Cl. All right, well, I'll go ahead and do the other part. So mass of Cl2 to the moles of Cl2 to the moles of C2H5Cl to the mass of C2H5Cl. All right. So we need to do each of these calculations. So we'll start with that 125 grams of the C2H6. All right, so we've got 2 times 12.01 plus 6 times 1.01. And that gives us 30.01 0.08 grams of C2H6 per mole of C2H6. Moles to moles, all of these are 1 to 1, so we'll do 1 mole of this per 1 mole of that. So 1 mole of C2H5Cl per 1 mole of C2H6. And then finally, moles to mass. We need the molar mass of C2H5Cl. So again, I'm going to clear this. I'll do 2 times 12.01 plus 5 times 1.01 plus, let's see, chlorine is 35.45. So we only have one of those. So I'll just put 35.45. And we get 64.52. So 60, oh, I put it on the bottom side. I need to put it on the top side because I want the moles to cancel out. This is why it's always important to write down these units. So 64.52 grams of C2H5Cl per mole of C2H5Cl. All right, let's go ahead and do dimensional analysis. Our grams of C2H6 cancels out. Our moles of C2H6 cancels out. Our moles of C2H5Cl cancels out. And that's going to give us 125 divided by 30.08 and then times 64.52. And we get, let's see, 3 sig figs, so 268. So we'll put 268 grams of C2H5Cl. Now again, we don't know if that is our theoretical yield or not. We need to do the other calculation before we can declare that that is our theoretical yield. All right, so let's do our mass of chlorine. Our mass of chlorine was 255. So 255 grams of Cl2. We'll need the molar mass of chlorine, so 35.45 times 2 gives us 70.90. So 70.90 grams of Cl2 per mole of Cl2. And then 1-to-1 ratio here in our balanced equation. So 1 mole of C2H5Cl per 1 mole of Cl2. And then finally, for moles to mass, we'll use the same molar mass that we had up here. So 64.52 grams of C2H5Cl per mole of C2H5Cl. And that's going to give us some number. Let's go ahead and do our dimensional analysis. Grams of Cl2 cancels out, moles of Cl2 cancels out, moles of C2H5Cl cancels out, and that's going to give us our grams of C2H5Cl. So 255 divided by 70.90. Go ahead and hit enter there. All right, and then we're going to multiply by 64.52. So times 64.52. And that gives us 232.05. And as we had previously, we have 3 sig figs. So we're just going to call that 232 grams of C2H5Cl. All right, when we look at those two numbers, we're going to play the game. Which one is smallest? All right, that is the smallest. That's not a very exciting game, but it's fine. That means that this is our theoretical yield. All right, and that means that this was our limiting reactant. All right, and then in case you're curious, that means this was our excess reactant. Okay, so that is how much we should get. That is how much we should get. But you know how this works. That's not usually what we actually get. Often when we're doing reactions, we get these secondary reactions. It just so happens that the product, the C2H5Cl, can react with another molecule of Cl2. And when it does, you end up getting the C2H4Cl2. And it turns out that can react with another molecule of Cl2, and it gives you C2H3Cl3. The point is that the more of these side reactions that occur, then the less of our actual product we're going to get. So let's calculate the yield, and our yield, so percent yield, is going to be the actual yield, which is given there, divided by our theoretical yield times 100. So in this case, our actual yield was 206 grams. Our theoretical yield is 232 grams. We want to multiply by 100 to make that a percentage. And let's clear all this. So 206 divided by 232, and then multiply by 100. And we have 3 sig figs, so we're going to call that 88.8. All right. So the reason that we care about this is, let's say you're a company and your goal is to make this product C2H5Cl, and you're going to sell that. Let's say these are kilograms instead of grams, and let's say you're going to sell it for $100 a kilogram. That would be a lot. That's way more than this would be worth, but just theoretically, right? And so if you made this much, $100 a kilogram, if you made 232 kilograms, that would end up being, what would that be? That would be what, $23,000. Okay, so that would be how much you thought you maybe were going to make. However, if you actually only make this, you actually only make $206,000, or I'm sorry, $20,600, so $20,000, and that's a difference of what, about $26,000, and that just kind of gives you an idea of why we care about this, because that doesn't even mention your margin. Your margin may only be 10% on this, and if you lose 12%, you may end up losing money on this. In addition to that, the more of these byproducts you make, the more of that you have to dispose of. And so you have to come up with a way to either get rid of that or sell it to some other person. So the reason I mention all of this is that there are chemical engineers. This is a job within the industry. There are chemical engineers who take reactions like this and they optimize them, and they get, the 88.8% yield. They may try to eke that up to 93, 94% yield. And if it's in a really big scale, that could mean thousands or hundreds of thousands or even millions of dollars for that company. So, and it also has an impact on how much waste has to be disposed of, and that has an environmental impact. So there is a big deal in understanding yield and optimizing the yield. So, all right. Well, that, I believe, let's see, that is the end of chapter 3. So we are done with the chapter 3, and so there we go. All right.